Welcome guys to this video. We are going to talk about orbital diagrams as they relate to electron configuration. So before we begin, let's talk about orbital diagrams. Orbital diagrams are just simply a way that we can visually represent the electron configuration of a particular element, specifically the spin of electrons that are part of it. We know from previous material that electrons are going to repel each other, meaning because they have the same charge, they are trying to stay away from each other as much as possible. So because of that, we can make the assumption that electrons, if they are in close proximity, they are going to be spinning in opposite directions. And that has to do, like I said, to do with the fact that they have the same charge and they are going to repel each other. So before we begin looking at some orbital diagrams, I want us to go over some important rules. And on this particular slide, what we're going to look at is the long version, much wordy version of each of these principles. But it is important for us to be able to see them. And then right after that, we're going to look at like more of a simplified version and some examples, because if we just look at definitions, sometimes they don't quite make sense. So let's start with Aufbau's principle. Right here, we have the definition that each electron occupies the lowest energy orbital available. That means that we always have to go in order from lowest to highest energy level. Then we have Hund's rule. In his rule, he stated that single electrons that have the same spin must occupy the same type of energy orbital before moving on to the opposite spins. And like I said, we'll look at some examples in just a moment. But basically what this tells us is that we need electrons to be single, and then once we run out of energy orbitals, we need to then start coupling them up. Last, we have Pauli's exclusion principle, which states that a maximum of 2 electrons may occupy a single atomic orbital, only if it has 2 opposite spins. So Pauli basically just said there's a maximum of 2 that can go in each of the orbitals. So what is an orbital? Because before we go and simplify some of these definitions and principles, we need to know what an orbital diagram is. And contrary to what most people think, an orbital is not necessarily that circle, right? Like an orbit. It has to do more with just a visual representation. And here on screen, you guys will see that is squares. So like one of the principles, remember, Pauli's exclusion principle says that a maximum of 2 can go in. So if you look on your periodic table, let's look at the 2s sublevel. So we know that in 2s there are 2 elements, lithium and beryllium. And if that exclusionary principle tells us that there can only be 2 for each of the orbitals, then that means that if we were to look at these 2 particular ones and the electrons that they represent, we could have both of them inside of one of the orbitals. And that's the reason why here on screen you see this specific number of squares, orbitals. So remember, any s sublevel can have a maximum of 2 electrons, right? So that means that any s sublevel will have only 1 orbital. But if you remember, the p sublevel can have 6. So if we are fitting 2 electrons in each of these orbitals, then that means that we're going to have a total of 3 orbitals. And if you look at the d sublevel, you will see that it can have up to 10. And that should tell you that because we can fit 2 in each, we are going to have a total of 5 orbitals. If we look at the f sublevel, we'll see that it has 14 electrons. So then that means that it can have a little bit more, right? It can have 7 because we can fit a total of 2 electrons in each of the orbitals. So that's where these particular orbitals in this specific arrangement comes from. All right, so now, like I said before, let's look at the different rules and principles. And here on screen, I have a few examples. So let's go back to Aufbau's principle. He pretty much said we go in order, lowest orbital first. So right here in this first example, we have 4 electrons, and the arrows represent the electrons and the spin, the direction of their spin. And you can see right here that this one right here, this orbital, the second orbital was skipped over. And that's violating Aufbau's principle. We can't have that. We have to go in order from lowest to highest. And we're going to assume that the left is the lower one. So in order for us to fix that, on the right, here you have what it would look like. So if we have 4 electrons, you're not going to skip over a single orbital. You have to go in order. So we would do 1, 2, 3, 4. The last one would just simply blink. Now, Hund's rule says that we are going to fill in all of them as singles before we start doubling. So right here on this first example on the wrong side, we have a total of 6 electrons, right? 1, 2, 3, 4, 5, 6. Now there are 5 boxes. And if you notice, there is an empty box that one of these electrons could have actually gone to. And you might be thinking, well, why are we doing this, right? Why do we have to keep them single? Well, remember, electrons are going to be repelling each other, and they're going to try and stay away from each other as much as possible. So with that idea in mind, when we represent them on paper using these orbitals and these arrows, we want to express that exact same information. We want to make sure that what we are showing on paper represents that idea. And right here, if you were to draw this, you're telling me that these 2 electrons prefer to be together versus that whole idea of repulsion, where one of them is going to want to be on its own orbital in its own section. So that's exactly what's happening here. So in order for us to fix that, right here on the right, you have what it should look like. Now, if you notice right here at the very first energy level, what you have is simply the idea that, well, because there's a total of 6 of them, at some point, one of them is going to have to start coupling up. So because you ran out of boxes, you're going to kind of revert back, because remember, you have to go back to the first orbital. So, and remember, they have to be in opposite spins. So you have to draw it in the first orbital. You wouldn't just draw it right here in the middle. You can't do that, because that's violating Aufbau's principle of you always have to go in the lowest orbital first. Now, Pauli's exclusion principle again says that no more than 2 electrons per orbital. So you can never draw more than 2 arrows in any given orbital, assuming, of course, you've already filled up all the empty orbitals before. Now, another part of Pauli's exclusion principle says that they must have opposite spin. And like I said, this is just the idea that electrons are going to repel each other and going to be having opposite spins because of that repulsion. Now, on paper, again, we show that with the arrows in the direction that they're pointing. So here in this first example, you have the 2 arrows that are pointing up, and that is violating Pauli's exclusionary principle. Also, even if you drew one going down, at that point you now have 3 of them, and that again still violating Pauli's exclusionary principle. So the way you would fix that, you would just make sure that the arrows are pointing in opposite directions. So, in pretty simple terms, Aufbau's principle, start at the beginning on the left side, go one by one. Hund's rule, keep them single for as long as possible. Once you run out of boxes, go back and start filling up, reverting back to the first on the left. Now, Pauli's exclusionary principle, no more than 2 per orbital, and we also want to always point them in opposite directions. Now, how does this relate to electron configuration? So right here on screen, you have the electron configuration of bromine, the long one, not the noble gas. And you'll see that they kind of match up. So the 1s2, right? 1s, and there are 2 electrons, there are 2 arrows. I'll skip over 3d10. So here's a 3d, and they are supposed to be 10 electrons. So 2, 4, 6, 8, 10. So this entire section right here represents visually that 3d10. Now this last portion, 4p5, we have the 4p right here on the right side, and there are 5 electrons in it. So there are 2, 4, 5. So it is an exact replica of the electron configuration, which is why it's so important for you to understand how to write the long version of electron configuration and not just be familiar with the noble gas. Because if you only knew noble gas, you would miss out on this entire first section that is very important for you to be able to visually represent the spin and the location of the electrons on an atom. Now let's do some practice. Now you might be thinking, okay, so how do I want to do this? Well, I have a couple of recommendations. One of the easiest ones, but also the one that kind of takes a little bit longer, is to just count the arrows. Because if you notice on that previous example, each of the arrows represented these numbers right here. And if you were to add them all up, they should give you the number of electrons that bromine has, so that it's 35. So if you were to sit and count every single one of these arrows, it would give you 35. And that gives you the atomic number for bromine, because we're assuming that all of these elements are neutral in charge. So you could do that here. You could count each of these individual arrows, and I mean, that works, right? Because you're just counting, and that tells you the atomic number. But when it comes to something like this very last example at the bottom, that's a lot of arrows, and it's very easy for you to make a mistake. So let's just try that for the first one. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have a total of 10 arrows, so that means atomic number 10. So that means that we are talking about neon, right? Okay. Now, on the second one, I don't want to do that because it takes a little while. So what I'm going to do is that I know that this entire electron configuration is a pattern. So what I'm going to do is I'm just going to count for my S sublevel, because I know that that's going to tell me the energy level. So I know that this first one right here, because any single orbital like that is going to represent the S sublevel. So I'm going to count, this is 1s, this is 2s, this must be 3s, and this is 4s. So I already identified that anything past here is going to be on the fourth energy level. So I know it's 4s, d, and then p. So I'm going to just look at the four energy level, and then in the d sublevel. So that tells me that this is 3d, because remember, it drops 1. So who is 3d? 1, 2, 3, 4. So I would just look at my periodic table, look for 3d4, and that would tell me that it is chromium. So here at this point, I want you guys to pause the video, finish up the last two examples, use either one of the two methods that I just showed you, and make sure that you check your answers on the next slide. All right, guys, so hopefully you took a moment, you looked up the last two examples for calcium and gallium. Like I said, either one of the two methods, it's fine. If you just want to count arrows, go for it. If you want to kind of figure out, okay, which of the energy levels am I at, and then go from there and count the arrows, you can do that as well. Either method works just fine. But this is kind of working from, I give you the orbital diagram and you have to find me the electron. Now let's look at trying to write them ourselves. So my recommendation here is going to be, first, write the electron configuration, the entire electron configuration, and then simply write the orbital diagrams, because you know that any S sublevel is going to have 1 orbital, P sublevel is going to have 3 orbitals, D sublevel is going to have 5, and then the F sublevel is going to have a total of 7. So if you can write the electron configuration of the elements, then all you have to do is draw, depending how many orbitals you need, and then draw in the arrows following the 3 rules that we saw at the very beginning. So at this moment, please pause the video, go ahead and attempt these 4. Again, write the electron configuration and then draw the orbital diagram. So hopefully you were able to take a moment to draw the orbital diagrams of these 4 elements that I have here. Like I said, it's my recommendation to always start with the electron configuration and then just simply draw the orbital diagrams and fill in with the arrows based on the rules that we learned at the beginning. Next video that we cover is going to be on the Lewis dot structures. That is another representation of the electrons and the configuration that they have within an atom. Thank you guys for watching.